All right, here we go. So last time we talked about the Fourier basis. And so
These are a cute color.
with this set of functions here, and it's an infinite basis, and it's an orthogonal basis. So with respect to this inner product that we defined using the integral, we can show it's orthogonal. So with respect to the inner product, what that means is when the functions are different, the inner product is 0. And when the functions are the same, then the inner product is not 0. And so there's a theorem in linear algebra that says orthogonality implies linear independence. And so the orthogonality gives us linear independence. And from the linear independence, we can use that to establish that this is a basis, for the space of continuous functions. So I think this example here, and the idea is to take a function and try and write it as what I call the trigonometric polynomial. Technically, this is not a trigonometric polynomial. Trigonometric polynomials don't necessarily, they usually just go to a finite number. So the partial sum of this series on the right-hand side technically would be a trigonometric polynomial. Just like, technically speaking, a power series isn't a polynomial since the degree goes to infinity, but certainly the partial sums of a power series are polynomials. We want essentially on the right-hand side, what you should keep in mind is that we don't know these coefficients. These are constants. And just like a Taylor series, we want to find a formula for these constants. So, and that's where the orthogonality really helps big time, so that's what makes life easy here with the orthogonality. So I'm just doing a toy example. I want to find the coefficient for A8. So here, when n equals 8, let me multiply both sides by, so n is 8. So let me multiply by cosine of 8z. Why cosine? Because those are the coefficients of the cosine basis functions. If this is B8, I'd multiply by sine of, 8, a sine of 8z. And if this was B7, I'd multiply by sine of 7z on both sides. And then we integrate. And the integrals, because of the orthogonality, the majority of the integrals, in fact, all but one integral on the right-hand side completely disappears. And so here, after integrating and because of orthogonality, we just have this one integral survives. And remember, we're looking for this constant A8 right here. So it's a constant, we could just pull it out of the integral and isolate the integral. And so we get this formula, which we can write in terms of the inner product and the norm, the the L2 norm. So the reason I wanted to write, certainly we could have stopped right here. We could have just stopped with this formula and said, okay, we can generalize that to sines and cosines of other basis functions, cosine 9z, 10z. We can generalize that to cosines and sines, no problem. But, I then write it this way, because this is a more modern way of looking at it. Maybe Fourier would have written it this way, but now doing modern mathematics, we want to write it this way and do it in a more modern style. And so here, what we want to recognize is on the, this formula here is a projection formula. And that this technique in general can be used in general anytime you have an orthogonal basis. So now I want to basically redo this example that we just did on the previous slide. I want to redo this, but completely abstractly. Where here now, and I'm going to do it in the finite setting just to make life easy, but this can generalize to the infinite setting, countably infinite. So here we start with a finite orthogonal basis. Okay, so let's just stop for a second and ask ourselves what that means. So start with the basis part. The basis means I can take any vector in the vector space, take any vector in the vector space, and write it as a linear combination of the basis elements. So when I say linear combination, I mean a scalar, and then in this case, times the basis vectors. So this would be a linear combination of the basis vectors. And so any vector in the vector space can be written as a linear combination of the basis vectors. That's what the basis part means. The orthogonal part means that if we take an inner product of the basis vectors, the inner product will be 0 if the basis vectors are different. The inner product will not be 0 if the basis vectors are the same. And we'll talk about the orthogonality. You'll see it in action here in 1 second. The other thing here to keep in mind is, we want a formula for this coefficient right in front here. We want a formula, and that's called a coordinate, that scalar, that real number v sub I. So, okay, first let's do the,
Professor?
yeah, go ahead.
When we're setting up our basis, is our basis limited to, can we have like repeated information in the basis? So it's like an overdefined basis.
So no, you can't. So by definition, the basis has to be linearly independent. And so if we have repeated functions in our basis set, then it's not linearly independent anymore.
Okay, so we can't have a basis that's like sine of x and 2 sine of x.
No, that would be redundant. You can have either sine of x or 2 sine of x, but both of them would not be allowed. Because everything is closed up to linear combinations. So 2 sine of x, since it's a scalar multiple, it's basically, from a basis point of view, from a span point of view, it's basically the same as just sine of x.
Okay, thank you.
Of course. So here, and the number of basis elements defines the dimension. Okay, so in this specific example, we're dealing with a vector space that's dimension capital N. In the case of the Fourier coefficients, we have countably infinitely many of them. That's why we're in a countably, a vector space of countably infinite dimension. So yes, let's pick a basis vector, e sub j. So here j is just some fixed number, like e sub 2 or e sub 3, whatever you like. And now we're going to take the inner product of v. So here, keep in mind what I'm trying to do. Keep in mind what I'm trying to do here. We have this vector v that's written as a linear combination. And I'm trying to now find a formula for the coordinates, these scalars that are right in front here. Okay, so right now, I don't know. I mean, we can guess the formula from the previous example, but right now we don't know a formula for that scalar right in front. It's called the coordinate. Okay, so we take v, take it with the inner product with e sub j, where j is fixed. So like v inner product e sub 2 or whatever. And then I'm going to replace v. I'm going to write it as that linear combination. And now let's expand the notation here. So I expanded the sum. So careful now. Just look at it carefully. And so now the inner product has a property known as bilinearity, which basically means I can now distribute this e sub j across the sum. And the bilinearity also allows us to pull out the coefficients. So, that's what I'm going to do. So now if you look very carefully, we have here's an inner product. And what's happened? Well, I distributed the e sub j to that inner product, right? And then I factored out, or I pulled out, in factor out, I pulled out the V sub 1, right? That gets pulled out here. And I'm doing that for every term, right? E sub j distributed to the V sub 2, E sub 2 term, pull out the V sub 2 plus E sub j distributed to the E sub 3 term times V sub 3, pull out the V sub 3. And so we kind of decompose the inner product into a sum of inner products. And now the orthogonality kicks in. So this is really important to appreciate the orthogonality. It's really important that the orthogonality tells us that if the basis vectors are different in the inner product, then it equals 0. And if it's not different, then it equals some number, which we call here norm E sub j squared. That's just the notation we use for a vector inner product with itself. So yeah, everything, you know, zeroes out. And at the end, we've just got one term left here on the right-hand side of our equation. And then, you know, on the left-hand side of our equation, we have that inner product. And now remember what we're trying to do. We want to solve for the V sub j. So dividing by norm E sub j squared, we get our projection formula. So now if you replace V with a function f and replace the basis vector E sub j here with a Fourier basis element, then you get exactly the formula we had on the previous slide. F of x, inner product, f of z, excuse me, inner product, cosine 8z over norm cosine 8z, 2 norms squared. It's the same formula. So this is called the projection formula. We can extend this to an, you know, countably infinite basis. And this is the formula we're using for Fourier series. Essentially, we can play the Fourier series game with any orthogonal basis. The Fourier series in particular has some really nice properties, you know, that we'll talk about. You know, if you think about cosine and sine from point of view of differentiability and continuity, these are really nice functions. And if you think about data, do we want data that's not continuous and, you know, kind of jumping all over the place, or would we like data that's more continuous, more manageable, more predictable to some sense if it's continuous, you know? So anyway, I'll come back to that point in a short second here. So here's the definition of a Fourier series. If you accept, you know, that we do have this orthogonal Fourier basis of the continuous functions, then by the previous result, the projection formula, because of orthogonality, we can, you know, we can create a Fourier series out of a function using those formulas. Right now here, I want you to be very careful because I'm making an assumption here that the function equals its Fourier series. And I say here, assume that f of z is in the proper space of functions. And so we'll talk about that very, very shortly next time. So if f of z has some nice type of continuity properties, we will be able to prove convergence. Right now, here I'm assuming convergence. Okay, so be careful. Here I'm assuming convergence. And so yeah, if the Fourier series has this form where we have these formulas for the coefficients, you know, essentially it's the projection formula here using the orthogonality. And so if you look back at that example, when we solved for a sub 8, we got exactly this formula. F of z cosine 8z over 2 norms squared of cosine 8z. And so, you know, it's just, this is a modern way of writing the formula, and this is a more classical way of writing the formula. Fourier would have written it in this more classical form. But of course, we're approaching this using a modern style of mathematics known as linear algebra, the vector space theory. I mean, that's the correct way to do it. Notice that the coefficient in the front, the a sub 0 coefficient, when we calculate, you actually calculate the coefficient here, we get a formula in calculus that we have defined to be the average value of the function. So, here I think it's really important at this point to let's conceptually think about what we're trying to do here. On the left-hand side, I have a function I'm trying to approximate, right? On the right-hand side, we have the approximation. So here, if you think about how does the right-hand side work, it starts out with a base value, right? If you zero out all the other coefficients, it starts out with a base value that's the average of the function. And now when you supply the z information, now when you pick an actual z value, that goes in here. It's really the rest of the Fourier series here that's now moving into position to compensate from the average. So maybe if the value at z for the original function is above the average, then somehow the Fourier series adds enough value to increase the value of the right-hand side. If f of z on the left-hand side is less than the average, then somehow the Fourier series reacts to decrease, add a negative number to the average to decrease the value. So try to kind of understand here what's happening on the left and the right. And there are some issues here, there's some issues that I want to bug you about now. For example, if we look at the function on the right side here, this function is a sum of periodic functions. Cosine and sine are periodic, and I'll talk about this more. So I'm just kind of introducing the idea. So these are the analytic issues of Fourier series, and these are the questions we want to answer first before we solve any PDEs. So the function on the right-hand side is periodic. Okay, remember a constant function is periodic, right? It's the most periodic function you could ever imagine, right? A constant. So the constant's periodic, cosine and sine, they're all periodic. So the function on the right-hand side is periodic. The function on the left-hand side may not be periodic. So we're comparing and contrasting these functions, what's on the left, what's on the right. The function on the left-hand side is defined only for minus pi to pi. The function here, our Fourier series, cosine and sine, this is defined for minus infinity to infinity. The function on the right-hand side, the Fourier series, this thing is infinitely differentiable, right? Isn't that a really nice differentiable continuous function? The function on the left, we don't know about the differentiability. We don't know about the continuity. We don't know. We just said there's a function f of z defined on minus pi to pi. We know, okay, maybe it's continuous to some extent. We can integrate it, right? When we multiply f to a trig function, that needs to be integrable. So there's some amount of continuity, but we don't really know what's going on. So of course, these are the analytic issues that we will address.
I have a quick
yes,
question.
please go ahead. Yep.
In the denominators for the Fourier coefficients, what
Yeah.
do the subscript and superscript mean, the twos?
So the subscript is referring to that we call the inner product that we're using. The inner product that we're using is called an L2 norm. So this is referring to the type of norm we're using, an L2 norm. If I was taking a 2 norm of a vector in a finite dimensional vector space, here when we write 2, we're not, this is where we're implying this is a vector in a finite dimensional vector space. And that here we're squaring the components. So this might not be, this could be an Rn, this could be an Rn. So here we're squaring the components. So here the 2 says L2 just to kind of indicate that it's a 2 norm, and the square is that we're literally just squaring it. Here, this is a square on top because the norm is technically defined as the square root of the inner product.
Right. Okay, got it. Thank you very much.
Yeah, so the 2 at the bottom specifies what kind of inner product. And here we're squaring to get rid of this square root. So yeah. And so now I want to, just compare Fourier series and Taylor series. So remember that this is a Fourier series class. So I have to spend some amount of time bashing Taylor series and saying how much Taylor series sucks and how awesome Fourier series is, right? So this is that part where I'm going to bash Taylor series. Okay, so all the Taylor series people who love Taylor series, don't take it personally. It's not my fault. Taylor series sucks. There you go. Okay. So Taylor series, as you remember from Calc 2, your favorite, it's a power series. And here, notice the notation I'm using for the left-hand side. So given a function, we can generate the Taylor series, which is a power series. So here, the only thing that's unknown is the coefficient C sub n. And we can prove in calculus that if a function can be represented as a power series, then the coefficients would have to have this as the formula. So what's the procedure? You give me a function f of z, I calculate the derivatives, evaluate it at a, figure out this coefficient, plug it in here, there's our Taylor series. 2 questions that we have to ask always when you're dealing with the series. Number 1, does it converge? Number 2, what does it converge to? So that's the reason I wrote this notation here for the Taylor series. The big question is, does this actually equal f of z? That's the question. That's supposed to be a letter F, but it was not successful. And so the big question is, are these equal? And so if you do some complex analysis, which I think some of you will next semester perhaps, we say a function is analytic at a point if and only if it equals its Taylor series. So, right off the bat, to use Taylor series effectively, we need to be ideally working with analytic functions. And for analytic functions, in terms of their convergence, okay, the convergence is typically restricted to a radius of convergence that's centered at the number a. So these Taylor series typically have a thing called a center. And so, it depends how nice the Taylor series, like the max series for e to the x is super nice. Its radius of convergence is all reals, but in general, that may not be true. So if this is a, then our interval of convergence is some interval here going out some distance. And I think if we call the radius of convergence capital R, then this would be a plus capital R. This would be a minus capital R. Anywho, inside the interval of convergence, awesome, great convergence. Outside, not so awesome. Outside, no convergence, So that's kind of, it is what it is. That's just how Taylor series are. If it's a good thing or a bad thing, it's up to you to judge. It's not a thing to judge, really. There's no good or bad. It's just math, damn it. So yeah, the other thing to keep in mind here is the formula for the Taylor coefficients we find by differentiation. So this puts some analytic requirements, some regularity requirements on the function f of z. So f of z needs to be at least differentiable. So when I say regularity, I mean, is it continuous? Is it measurable? Is it differentiable? So here for Taylor series, for this to even make sense, right off the bat, these derivatives need to make sense. So we're asking for a lot of smoothness for a Taylor series. And one final bash against Taylor series, the basis is not orthogonal. It is a basis in that it spans and it spans and it's linearly independent. So those are the two requirements for being a basis. Basis should be linearly independent and basis should span. So here it spans and it's linearly independent, but it's not orthogonal. You know, if you take an inner product, we don't have a nice orthogonality. And, you know, so using the Gram-Schmidt process, you can create an orthogonal basis consisting of polynomials called the, what they call Legendre polynomials, the Legendre polynomials. But, you know, that's not what we're doing in this class. So, okay. So now let me tell you why Fourier series is so awesome. And we should never, ever, every time we see a Taylor series, we should just say, oh, that's horrible. Okay, so Fourier series. So first of all, I'll just remind you, here's the Fourier series of a function f of z. Please note the notation, observe the notation here. So that says I found the Fourier series of the function f, and it, you know, it's a function, it's independent variable is z, it's dependent on z. And then on the right hand side, we have the Fourier series where the only things we are always only calculating, anytime we find a Fourier series, the only things we're ever calculating are the coefficients. And we're using the projection formula to calculate those coefficients. So when we actually talk about the convergence, I'll show you, or we'll see that when the Fourier series does converge, it converges for all reals. There's no concept of radius or of convergence or interval of convergence or anything like that. So, you know, from that point of view, it's nice, you know. The Fourier coefficients can be found by integration and not differentiation. So we don't require the function to be differentiable. We require it to be integrable. And it's so the requirements for integration are a lot looser than for differentiability. I mean, if you really want to get, you know, very measure theoretic, the functions really just need to be measurable. You know, we'll require that they be continuous, but that's really even more than we technically need. We just need to be able to integrate them. Conceivably, even if it's a function that's not integrable, we can just approximate an integral and try and fashion together a Fourier series and see if it does anything. You know, you can even try this trick with functions that don't behave well. Just like try to approximate, you know. So the Fourier basis is orthogonal, and so that's nice for not just finding the coefficients, but doing calculations in general. You know, I won't go into the kind of all the numerical analysis kind of aspects of Fourier basis and stuff like that. So just some terminology here for a Fourier series. Of course, in practice, we don't use all infinitely many terms. We're only human, so we can't do that. In practice, what we do is we look at the Fourier series going to some, you know, ideally large number up here. So I'm gonna, instead of looking at the full Fourier series, we'll look at this truncated Fourier series that'll go to some, you know, let me call it m. This goes to some positive integer, large positive integer m, and we call that truncated Fourier series is this f tilde sub m of z. It's just like the Taylor polynomial, right? You have the Taylor series, which is the full-on series, but then if you cut off the Taylor series, then you would get what's called the Taylor polynomials. And that's what we're using in practice. That's what we're working with in practice. So, you know, questions to think about here. The old right-hand side is, you know, infinitely differentiable. It's periodic. It's defined for all reals. The original function that we started with may not be any of those things, you know. So what's going on here? What exactly is going on with the Fourier series? What exactly is the right-hand side, you know, doing, right? So let's do an example here. So I picked our favorite absolute value function. So here f of z is the absolute value of z, z between minus pi and pi. You see the graph there, I graphed it. And so let's find the Fourier series. So, you know, let's be very clear, all we're doing is finding the coefficients, right? So let me find, I need to find the b sub n coefficients, the a sub n coefficients, and a sub 0. Let me show you, let's get rid of b sub n right away. So first of all, I'll just remind you the formula, right? So here's the projection formula to find the coefficient. Here's in the integral version, whichever one you like. I mean, we should know them both, I guess. And so now we use some good old fashioned Calc 1 geometry. So the absolute value is an even function. Sine is an odd function. Even times odd is odd. So here we're integrating an odd function over an interval of the form minus a to a. And calculus tells us, the net area is 0. The area above and below, I should say that, they cancel out. And so for our Fourier series, the b sub n terms are all 0. So let me back up one slide. For a Fourier series, for that particular example of the absolute value, that's completely gone. There's no b sub n term. And it makes kind of sense to me because the sine function is odd, and the sum of odd functions. So here the odd component here has completely disappeared because the absolute value function is not an odd function, so that's maybe not a coincidence. So now we need to find the a sub n terms. So the a sub 0 term, the formula is slightly different. We divide by 2 pi instead of pi, okay? And that has to just do with the geometry of how the integral works, okay? And so here, you remember how we integrate an absolute value, we have to break up the domain. So I break up the domain minus pi to 0, and the definition of the absolute value there is negative z, and then integrate 0 to pi. So I've broken up the domain. Definition of absolute value between 0 and z is just z. And then you can integrate both of them and, or use symmetry, right? We could have also used symmetry. I could have just integrated one side and multiply by 2. So yeah, we get that the average value here is pi over 2. And for the coefficient of the cosine term, so now for the a sub n terms, okay? So for the even a sub n terms, so a2, a4, a6, those turn out to be 0 using integration by parts. I'm not going to show you the details of the integration. That's something that might be good for you to practice. And what are you integrating? We're integrating absolute value of z. It looks similar to this. We're integrating absolute value of z, but instead of a sign here, so hold on, let me get rid of this sign. Instead of a sine nz, now let me pencil in a cosine here. We're going to have a cosine, and those would be the a sub n coefficients that we're trying to calculate. And how would you calculate it? You'd break it up, minus pi to 0, negative z cosine nz dz, and use integration by parts, plus integral 0 to pi z cosine nz dz, and use integration by parts. So for all the ones where n is even, n equal to 2, 4, 6, 8, you can show the terms cancel out. I think you get like a term, it's like 1 minus 1 to the n. So when n is even, that minus 1 to the n becomes 1, and the 1 minus 1 cancel, something like that. And so when n is odd, you get like a 1 minus 1, you get a negative number there. It's not 0, you can show, okay? And so here, we're now ready to cobble together our Fourier series. We just are going to take that linear combination of 1 cosine nz, sine nz, and put in the appropriate coefficients. All the sine terms are 0, they're all gone. For the cosine basis terms, only the odd ones have survived. And then there's the a sub 0 term in the front. So the Fourier series of absolute value of z looks like this. And so look at this in 2 steps and go slow. So first look at this part and stop. So there's your a sub 0 in the front. And then the rest of it is sigma m going from 1 to infinity, a sub m cosine of 2m minus 1z. It's all the odd cosine basis terms with the coefficient a sub m plugged in. So here, this 4 over pi, all this stuff is from the coefficient. I pulled out the -4 in the pi since it doesn't have an index on it. It's just a constant that's multiplied to every term. And so now we can look at the expansion. Take a look at the expansion now. You can see it's the sum of these cosine, we should think of each cosine term as a wave. It's the sum of this constant in the front, pi over 2, and then this, extended difference of waves of different frequencies. So things you should notice is we have a different wave number here, 1, 3, 5. So what's going on here? The way I like to think about it is think of a prism, right? When light goes through a prism, it gets broken up into its spectral parts. So this is a type of decomposition. I think of the Fourier series basis as kind of like a filter, and we're decomposing the function into different frequencies. So each wave number has information about the function at a specific frequency, and it's capturing the information about that function. And what's remarkable to me is that we're trying to approximate, in this case, straight lines with waves. It's one thing to approximate a cosine or sine, but absolute value of z. So some issues I want to always remind you about: convergence. And so here, let me tell you what I did here on the next slide. So if you just take a look at this part, what I'm going to now do is I want to check it for absolute convergence. I'm going to look at the series of the absolute values of all the terms, and I'm going to make this a plus, because I'm going to basically, I'm looking at, if you have sigma a sub n, I'm looking at sigma absolute value a sub n, because I want to check for absolute convergence. Okay, so that's one thing I should have maybe been more clear about on the next slide. So here, this series, that's the series of the absolute value of each term of the Fourier series added together. If this thing converges, then the original series converges absolutely. And so here's one nice reason, we like the Fourier series. All of these basis elements, cosine is bounded by 1. We can just make it disappear. We're doing a comparison, a direct comparison here. And here, save for the first term, all the other terms can be written in a pattern. It's the same pattern from the Fourier series, except we got rid of the cosine 2m minus 1 times z part. We took absolute values of everything and said that thing is less than this series. Now, this series, we can either compare it to a p-series or we can do an integral test. And by integrating, we can show the series converges. So by direct comparison test, the series of absolute values of the Fourier series, that Fourier series is absolutely convergent. So now let's not get too excited. We don't know what it converges to. Sneaky, right? So, by the way, and we'll talk about this more later, we can also, using just Calc 1 Riemann sum stuff, maybe now is a good time for me to, let me switch over here for 1 second. Oh my gosh, this is harder than it needs to be. Okay. Okay, so let's see. Here we go. All right, so here, the actual Fourier series, I don't quite remember what it is, but the actual Fourier series, if you think about this as being the 1 over whatever it is times a delta m, where delta m is 1, we can set this up to look like a Riemann sum. And we'll do this in more detail later. I'll put it on a homework in a couple of weeks. But just to remind you here, because we're talking about anytime you have an approximation, it's nice to also have some kind of error estimate, So, and here, since this is a decreasing function, you'll be able to set up a Riemann sum using right endpoints or something like that to where it looked like that. And then so we can interpret it as the lower sum of an integral. And so then, using our calculus theory, we can, so this is the Fourier series interpreted as a Riemann sum. We can bound it, we can compare it to some type of integral of 1 over, in this case, 2x minus 1 dx. Okay, so that's kind of, I've written some of the details on that without going into the geometry too much right here. So that's what I've written right here. So here, if we now take this function and look at it from m-1 to infinity, and look at the right endpoints and delta x equal to 1, then we can set up a Riemann sum and compare where this sum up here without the cosine and sine terms, this sum up here will show up as a lower sum for approximating the integral. And so then, in Calc 1, we used the Riemann sum to approximate the integral. Now we're doing exactly the opposite. We're using the integral to give us some information about the infinite sum, which really makes more sense, right? I mean, the integral is easy to calculate, the infinite sum is hard to work with. So using Riemann sum stuff, we can bound the Fourier series with this integral and calculate that integral and actually come up with an error bound that's dependent on m. M is where we are cutting off our Fourier series. Here, this is my error bound, so I should have maybe emphasized what's on the left-hand side here. This is the error bound of using the truncated Fourier series compared to the original Fouriers, and we can kind of get some error estimates, just like we do with Taylor series. So by the way, we know that it converges, but we don't know what it converges to, okay? So here, just for fun, I did some numerical experiments. I mean, I think that's now the right thing to do. Graphs are not a substitute for analysis, but they're definitely, fun to do. So here, what I did was I started with looking at f tilde sub 2. So that's the first 2 non-zero terms from the Fourier series for absolute value of z. And so in green is the actual function, and the dotted black line is the Fourier series, the truncated Fourier series. The Fourier trigonometric polynomial, I guess, is the right term, second degree Fourier trigonometric polynomial. And you can see it dances around the absolute value curve. It's undulating like a cosine curve or a sinusoidal curve, what we'd expect from a sine or cosine type of curve. And so let me add more terms. And so here I added one more term. You see it's starting to straighten out. So here I think it's important to think about what the Fourier series is doing. The waves are lining up so that they're interacting constructively and destructively, right? Peaks are canceling out valleys as necessary, or peaks are combining with peaks, or valleys are combining with valleys as necessary to start to assume the shape of the function we're trying to find the Fourier series of. It starts this way, looking more like a cosine curve. If I only graphed one term, then it would look like a horizontal line, right? It starts out looking like a horizontal line. And then as we graph more terms, the constructive and destructive interactions of the waves, and the Fourier series is figuring out how to do all this, right? We didn't pick the coefficients. We just used the projection formula. We just used the theory, right? It's just doing it itself. And so here I added 4 terms. It's already really super close, so let me go. You can see that. I don't know what's with that jump. It's because I added this thing down here. So yeah, without doing any analysis, it does look like the Fourier series does seem to be converging to absolute value of z. And to me, I always find it sort of endlessly fascinating that we're able to approximate straight lines with curves, you know, sines and cosines. I never get bored of that. Like I could do this all day. And I generated this to many more than 4 terms and looked at it, and it just, yeah, of course, gets better and better. So yeah, so we should talk about the convergence, and we should talk about what the Fourier series actually represents, you know, and I'll do that next time because I think it's pretty much oh no, it has 5 minutes. You know me, you know how I am. All right, let me talk for 2 minutes and then I'll stop. Oh, do I have 4 minutes? How much time do I have? Damn it. Now 4?
Yeah, 4 now.
So I've posted this next set of notes already, and we'll talk about it next time. But of course, if you want to read ahead, you can. You know, all of this stuff would appear on the next homework. It's not on any of this homework that's due on Friday. So let's see. So this is the second set of notes. So this is now covering Harvey Seeger's, you know, Harvey Seeger wrote these notes on Fourier series. So now we're in chapter 3, you know, and the real question is, what is the Fourier series doing? And I'll show you that there's a thing called a periodic extension that's happening here. If we graph the full Fourier series, this is the same Fourier series for the absolute value. You see, it does this thing called a periodic extension where it's repeating itself. You know, so next time we'll discuss the details of the periodic extension, and we'll get a real handle on what exactly is the Fourier series doing to the function on the other side. The way I like to think of when we take a Fourier series of a function is we're applying a treatment to the function. We're Fourierizing it, you know, and so the thing we get out is not exactly the function, but there are, you know, relationships to the original function. All right, everybody, I'm going to stop right here. I will continue with properties of Fourier series next time. I just want to thank you for your time and stop right here.